Hello, my name is David Egan. I'm a fourth-year mechanical engineer as well as the project lead and test pilot of the Unmanned Aerial System Robotics Club. My role has been to oversee the design and manufacturing of the flight vehicle as well as the integration of the subsystems. I've participated on the club since my freshman year, and my role on the flight line will be to oversee the assembly of the flight vehicle as well as the execution of the mission.
Hi, my name is Tom Kantner. I'm a third-year aerospace engineering student and the structures lead for Unmanned Aerial Systems. My role has been to oversee the design and manufacturing of the quadcopter and the individual subsystems. Prior to my 3 years experience with this project, I was involved in robotics competitions through the Technology Student Association of Pennsylvania. At competition, I will be responsible for the assembly of the flight vehicle and preparation for our mission.
Hi, my name is Carmen Morshid. I'm a sophomore here at UCLA and a second year on Unmanned Aerial Systems. I've been involved in robotics since high school, specifically freshman year. My team, Team 971 in FIRST Robotics, advanced to finals in the national championships multiple times, and that really sparked my interest for this field. Here on Unmanned Aerial Systems, I was the software lead this year, and I had a specific focus on integrated testing and deployment of our code both on our computers and to the drone when we're testing it out. On the flight line, I will be monitoring the drone and ensuring that missions are executed safely and efficiently.
My name is Ryan Nemiroff. I'm a first-year electrical engineering major. I've had a lot of experience with software and autonomous robotics, but preparing for the competition this year was my first experience with aerial vehicles. For the competition, I worked on the communication software along with a web interface for planning out missions. On the flight line, I'll be monitoring the ground station and ensuring the connection strength with the drone.
My name is David Thorne. I'm a first-year aerospace engineering student at UCLA. I have 3 years of previous high school FTC robotics experience, and I'm on the structures team here, focusing on the airframe and the gimbal systems.
This is our 2018 flight vehicle Spinny, a student-manufactured heavy-lifting quadcopter. It weighs 35 pounds with all subsystems mounted and is capable of flying for the full mission duration without stopping. The frame is manufactured from 2mm thick carbon fiber plates, which are sandwiched together to form separate trays for the motor arms, the various electronical systems, and the power management. The gimbal and payload systems are custom made to fit our drone and accomplish the tasks for the competition. The core of the electronic system utilizes a Pixhawk and a Raspberry Pi companion computer, which is running on the drone for the mission duration. The same system was also installed on 2 other small drones and a medium-sized drone to perform safety checks on controls before testing on the competition drone.
This year, our goal is to have almost all the software that we utilized be developed by the team. Our software system is tailored towards efficiently completing the mission. Our control system makes use of the Pixhawk flight controller, which communicates with Q ground control as well as our C++ controls code. The controls code utilizes the data stream from the Pixhawk to avoid obstacles and accurately zone in on waypoints. A rapidly exploring random tree algorithm is used to avoid obstacles. In maneuvering waypoints, the vector between the drone and its destination and the vector between the drone and the closest point on its designated path are combined to ensure that the drone will hug the path in case wind blows it off course. These algorithms can be run on the Raspberry Pi on the drone or on our more powerful laptops on the ground. Based on our findings, it is faster to run controls algorithms on the ground and then send the results to the drone through Wi-Fi. While Q ground control has proven to be invaluable, our custom-built ground station is just as important. Our ground station interface displays everything we need to know about the drone and automatically retrieves and overlays the mission details on a map. This makes it easy to design a mission plan and keep track of the drone's progress in completing it. The ground station has a separate view for monitoring image capture, and both views can be used simultaneously on different computers since we built the ground station as a web server. This new system has made it much easier this year to manage the completion of mission objectives. For our imaging system, a folder with images is synced between the ground and the drone, and new images are automatically queued to be processed using neural networks.
This year we will be attempting almost every task during our mission demonstration. Our primary objective is autonomous flight, including takeoff and landing. We expect our drone to be able to fly with minimal human intervention and within 100 feet of set waypoints, as well as stay within the bounds of the airfield. We will also be attempting to detect, classify, and localize the images received from our onboard camera by providing the judges with accurate descriptions and geographical positions of the emergent targets. Static obstacle avoidance will also be attempted by our team, where we hope to avoid the virtual stationary objects placed throughout the course. UAS at UCLA has developed a working payload drop system, and we expect the bottle to break on different surfaces such as grass, dirt, and concrete from cruising altitude when our flight vehicle reaches the desired location. In addition, we expect our drone to fly continuously without timeouts and complete the previously stated objectives in a timely manner. UAS at UCLA also plans to uphold our reputation as an organization by acting courteous and professional throughout the duration of the competition. Dynamic obstacle avoidance will not be attempted at this point in the development.
UAS at UCLA's rationale behind developmental testing was essentially this: test anything we can in simulation and on test drones before we put on the competition drone. The types of developmental tests that were performed on Spinny, our competition drone, include static thrust tests at our campus. These included strapping the drone to a static table and performing about 70% throttle bursts on the ESCs. This was to check both battery drain and verify the integrity of the system. For instance, whether the mechanical system would hold up or whether the electronics would suffer interference at high throttle. Over 1,000 autonomous flights have been performed in simulation with our control base, and this was made possible thanks to the usage of the PixHawk simulator and integrated testing with Travis CI integrated with our GitHub code base. And we wrote tests to run the PixHawk simulator alongside our code to make results from these tests as close to reality as possible. So over the entire competition, over 1,000 tests have been run because we've had over 1,000 changes in our code that have triggered these tests to run. On top of that, 10 autonomous flights have been performed in real life, 5 on our testing drone, 5 on our large drone. These flights have averaged between 5 to 10 minutes with about 20% manual flight accounted for during manual takeoff, manual landing, and manual override during flight. The reason we want to include manual control for this is just in case we do have to manually save the drone. That is the most critical path that we determined to making this drone very safe to land in the event that a control issue does arise. So we focused our testing efforts on ensuring that manual override worked very well. Tuning on Spinny involved many hours of looking at parameters for the PX4, and this included over 700 parameters ranging from the amount that the throttle will ramp up during takeoff, the amount that the RC is trimmed, and the minimum motor throttle speed during idle. We tracked all these parameter changes in one big spreadsheet for all our drones, small, medium, and large, and this allowed us to learn very deeply about what each parameter meant. And by the next test flight, we verified all those changes, talked them over, and then tested them one by one before we had all the changes applied to the drone. For tuning, we followed a very similar method to how we did parameter tuning on the drone. A subset of the parameters that required careful modification were, of course, the rate controller and the PID for position control. So we used flight logs to verify pitch, roll, and yaw rates during our manual and autonomous flights. And with these values from our logs, we proposed changes to the PID that were applied at the next test flight. For autonomous takeoff and landing, the main parameters we had to adjust were throttle ramp, minimum motor spin, and the height of the drone after it took off. For landing, we had to adjust the minimum throttle before disarm once it's landed.
We heavily tested waypoint accuracy with the PX4 simulator in order to create a robust path-following algorithm. After initial testing, we noticed that the simulator would overshoot waypoints and veer off the desired path, so we implemented an algorithm to correct for this. Several flights with our small test drone allowed us to make adjustments, such as tuning the threshold where the drone considers a waypoint reached and starts traveling toward the next. In a flight with the competition drone, we attempted 12 waypoints and recorded the error for each. On average, the drone missed each waypoint by 8.4 feet.
Our localization algorithm was evaluated using 50 images of 3 targets taken during test flights, alongside 10,000 computer-generated synthetic images of targets of various shapes, letters, and colors with backgrounds from aerial and satellite imagery. The overall performance of the algorithm was evaluated using 3 different metrics: the percentage of missed targets, the number of false positives, and the average discrepancy between the true bounds and the calculated bounds. When optimized to minimize the number of missed targets, our algorithm missed approximately 4% of targets with a rate of 1 in 20 false positives and an average discrepancy of 8 pixels.
UAS at UCLA has tested the air delivery system several times from multiple altitudes onto different surfaces. The payload has been dropped 7 different times, with the bottle breaking 4 of the 7 times, almost always on pavement. However, all of these drops were below the competition altitude, so we anticipate that the bottle will break from higher altitudes, and further testing is needed to confirm this. On average, the bottle lands within 10 feet of the target, but as previously mentioned, this was from lower altitudes.
We have performed one full mission test in which the drone attempted traveling autonomously to 12 waypoints. The payload was dropped manually onto the target location, and photos were automatically taken periodically throughout the flight. This test proved that the drone can accurately travel to waypoints, which is indicated in the data shown earlier. The drone also successfully dropped the payload on command, and this can easily be done autonomously as well. During the mission, we had comfortable control over the drone's actions. Manual takeoff was followed by a smooth transition to autonomous flight enabled by our ground station interface, and switching from autonomous to manual control and manual landing were also successful. We did not test object localization and classification during the mission because we were only capable of running our ground station system on one laptop. Object detection and classification has been thoroughly tested separately, and will be tested in a mission as soon as we get the opportunity to do so with necessary computing resources at the test site. Autonomous obstacle avoidance was also not tested, but the drone successfully followed a complex waypoint path, indicating that stationary obstacles would not be a problem. Although tested independently, we are confident that object recognition and obstacle avoidance can be successfully incorporated into a mission. Part of our testing philosophy is to thoroughly develop individual tasks before attempting them simultaneously. Several more mission tests will be performed, and these will incorporate all planned competition tasks. Autonomous takeoff and landing will be used for the mission after further testing and tuning of the PX4 parameters. During the mission, it was noticed that the drone jerked suddenly when changing direction to travel to the next waypoint. To fix this, we have added smooth acceleration by preventing the velocity set point from changing instantaneously by a certain threshold. We scored this test mission according to the rules, barring the minimum altitude penalty. The score is not entirely representative of our expected competition performance due to the fact that it was not full scale and we did not attempt all objectives, but it is useful in predicting our future performance. This test mission was performed over a very small area, so it was completed within 5 minutes and no post-processing was done, giving us a timeline score of 90%. Since takeoff and landing were performed manually, we had 2 pilot takeovers. The drone hit all waypoints with an average error of 8.4 feet, giving us an autonomous flight score of 88%. Obstacle avoidance and object recognition were not attempted in this test, so our score in these sections is 0. The payload did not release water upon landing because we tested at a low altitude, so our score for air delivery is also 0. On first contact with the ground, the payload landed about 5 feet away from the target, giving us a potential score of 97%. The team communicated effectively and had no issues as the mission was undertaken, so we assume a perfect operational excellence score. This gives us a total score of 45% for the mission.
At this point, UAS at UCLA has completed 1 full autonomous mission and a few more are scheduled before competition. Using the data collected from the first trial along with Spinny's performance and other test flights, we can estimate how our aerial vehicle will perform at competition. We believe that our quadcopter will be able to complete the mission in under 35 minutes, 30 minutes for flight and 5 minutes for post-processing time. With no timeout, our total score for the timeline section is 56%. Based on Spinny's performance in earlier trials, our drone has performed exceedingly well when it comes to autonomous flight and waypoint accuracy. With 100% waypoint capture and an average error of 8.4 feet, Spinny's capabilities show us that we will score high in this section. If we take 0 timeouts, the UAS at UCLA will receive 96% for this section. Static obstacle avoidance has also proven to work well at this point, with all the stationary test objects avoided 100% of the time. However, since dynamic obstacles will not be attempted this year, we anticipate receiving a score of 50% on the obstacle avoidance section. Our image recognition algorithms have proved to work extremely well in simulations, with our program successfully identifying the shape about 90% of the time and letters approximately 94% of the time. As we hope to increase these numbers even further during our testing, at this point we believe that we will score around 75% on this section. Our air delivery has proven successful both under autonomous and manual control, landing every time within 20 feet of the target. Our bottle breaks most of the time depending on the surface and height that the bottle is dropped from. Through more testing in the coming weeks, we are confident that the bottle will be able to break no matter what the surface is from the competition cruising altitude. For this reason, we believe that we will score at least 87% in the air delivery section. Finally, UAS at UCLA upholds the codes of conduct outlined by the competition, and we plan on receiving a perfect score for operational excellence. Tallying the totals from each of the subsections, we estimate that we will receive a total score of at least 78.1%.